Hyperconjugation. In this module, you will learn about hyperconjugation and its role in the stabilization of carbocations and molecules of alkenes. Let us begin the study of hyperconjugation by considering carbocations first. You must be aware that carbocation is a chemical species bearing a positively charged carbon atom with only 6 electrons in the valence shell. The simplest carbocation is methyl carbocation, having only one positively charged carbon atom which is linked to 3 hydrogen atoms. The carbocations are classified as primary, secondary and tertiary depending upon the link of positive carbon atom with 1, 2 and 3 carbon atoms respectively. Let's study about them one by one. First is primary carbocation, ethyl cation, which contains the positive carbon atom linked to 2 hydrogen atoms and 1 carbon atom of methyl group. The positive carbon atom of ethyl cation is sp2 hybridized. It contains 3 sp2 hybridized orbitals and 1 unhybridized empty p orbital. 3 sp2 hybridized orbitals form sigma bonds, 2 with 2 hydrogen atoms and the third one with carbon atom of the methyl group. The unhybridized p orbital lies perpendicular to the plane of the sigma bonds. The methyl group linked to the positive carbon atom forms 4 sigma bonds, 3 with the 3 hydrogen atoms and 1 with the positive carbon atom. As you know that carbon-carbon sigma bond is free to rotate, therefore one of the carbon-hydrogen sigma bonds of the methyl group gets aligned to the plane of empty p orbital of the positive carbon atom. Due to the free rotation of the carbon-carbon sigma bond, each of the 3 carbon-hydrogen bonds of methyl group once gets aligned with the plane of the empty p orbital of the cation, thus stabilizes the cation. The stabilizing interaction, which occurs due to the interaction between the electrons of a sigma bond with the adjacent empty or partially filled p orbital, is referred to as hyperconjugation. This concept of hyperconjugation was first discovered by Baker and Nathan, and therefore the concept is also known as Baker-Nathan effect. More hyperconjugation means more stability of the carbocation. Hence, the tertiary carbocations are more stable than the secondary carbocations, which in turn are more stable than the primary carbocations. The primary carbocations are definitely more stable than the methyl carbocation, which does not have any sigma bond adjacent to the empty orbital to exhibit hyperconjugation. So far you have learnt about the hyperconjugation in carbocations. Let's now study about the hyperconjugation in alkenes by considering the molecule of propene. Both the doubly bonded carbon atoms in a propene molecule have one unhybridized p orbital with single electron. One of these doubly bonded carbon atoms have one methyl group attached to it. The hyperconjugation in this case involves the delocalization of electrons of the carbon-hydrogen sigma bond of the methyl group to the adjacent singly occupied p orbital. Due to the free rotation of carbon-carbon sigma bond, all the 3 carbon-hydrogen bonds of the methyl group contribute towards the hyperconjugation, therefore making propene more stable. Just like the case of carbocations, more is the number of alkyl groups attached to the double bond of an alkene, more will be the hyperconjugation and more will be the stability of the alkene. Therefore, tetraalkylated alkenes are more stable, followed by trialkylated alkenes, followed by dialkylated alkenes, followed by monoalkylated alkenes, followed by ethene, which does not have an alkyl group attached to the doubly bonded carbon atoms, to exhibit hyperconjugation. In this module you have learned the stabilizing interaction which occurs due to the interaction between the electrons of a sigma bond with the adjacent empty or partially filled p orbital is referred to as hyperconjugation. Carbocation is a chemical species bearing a positively charged carbon atom. Carbocations are classified as primary, secondary and tertiary depending on whether the positive carbon atom is directly linked to 1, 2 and 3 other carbon atoms respectively. Hyperconjugation in carbocations results due to the interaction of the electrons of the sigma carbon-hydrogen bonds of the methyl group attached to the positive carbon atom and the empty p orbital of the positive carbon atom. Hyperconjugation results in the dispersion of positive charge of the carbocation and thus increases its stability. The stability in turn increases with the rise in the number of alkyl groups linked to the positive carbon atom of the carbocation. Hyperconjugation in alkenes results due to the interaction of the electrons of the sigma carbon-hydrogen bonds of the alkyl group attached to the doubly bonded carbon atom and the adjacent singly occupied p orbital of one doubly bonded carbon atom. As the number of alkyl groups attached to the double bond of an alkene increases, the hyperconjugation and the stability of the alkene will also increase.